Hi, my name is Tianyi Liu. I will present a picture, which is a benchmarking framework for Cloud 3D applications. This is a collaboration work of University of Texas at San Antonio and the University of Michigan. This is the outline of this talk. I will start with describing the background of a Cloud 3D system. For Cloud 3D system, it needs a client proxy and a server proxy to send the user input to the cloud and send the images back to the client side. The 3D application runs in the cloud and receives inputs from server proxy. 3D applications call 2D 3D functions and get frames rendered on GPU. When the frame is ready, it was copied from GPU memory to CPU memory, and then was sent to client side for display. With the popularity of cloud gaming, cloud VR, 3D applications are becoming a major type of workload for cloud and data centers. Unfortunately, there is limited public research on how to design cloud systems efficiently to support 3D applications. The main reason is lack of standard benchmarking infrastructure for this new era, like a benchmark suite and performance evaluation tools. There are three key challenges. The first challenge is to generate human-like inputs to interact with random objects in 3D applications. The second challenge is to track input processing and accurately measure performance of each component in Cloud 3D system. Third, as 3D applications are typically refreshed every 1 or 2 years, benchmarking framework should be extended to new 3D applications easily. Our goal is to develop an effective Cloud 3D benchmarking framework that can address these challenges. Now let me explain how we designed the picture to overcome challenges mentioned before. And let's begin from intelligent client. Instead of using human players, we would like an intelligent client to play games automatically, inspired by self-driving cars. First, we grab a game frame from screen. Second, we analyze this image using convolutional neural network and computer vision to detect key objects. Third, after the detection, useful information is imported into a recurrent neural network to generate an action for current frame. Finally, our intelligent client will simulate this keyboard event or mouse event, which will be sent to the cloud. Now, when we replace human players with our intelligent client, this figure shows the overall architecture of picture. Next, we will talk about the performance measurement framework. First, let's have a look at the sequential process for generating frame N. Stage 1 to stage 4 are input processing. Stage 5 translates drawing APIs into GPU instructions and get frames rendered on GPU. Stage 6 copies pixel data from GPU memory to CPU memory. And stage 7, 8, and 9 are related to frame transmission. Similarly, we can generate a frame N plus 1 in a pipeline manner. In order to get a performance of each stage, we inserted several hooks along the home process. When an event is received by the server proxy, an ID will be created, and the ID will travel through the home process along with the event. In the meantime, timestamps will be recorded by each hook function and printed out at the client side. Here, we use two standard metrics. RTT is the round trip time, and the throughput of frames as FPS, frame per second. To increase the FPS, the modern pipeline tries to generate a current frame and send the last frame in the same pipeline. When generating frame N plus 1, stage 1 to stage 4 are the same as before. The difference is stage 6 of last frame is executed before stage 5 of current frame. In this way, we can send a frame n and generate frame n and generate frame n plus 1 in the same pipeline. Similarly, we can send frame n plus 1 and generate frame n plus 2. Our performance measurement framework can also handle this pipeline. Now, we have finished the picture framework. I will move on to evaluation. We implemented our benchmark framework on TurboWinC and VirtualGL, which is a cloud 3D system based on remote desktop. In order to conduct a comprehensive evaluation, we also collected a cloud 3D benchmark suite, including 4 3D applications and 2 VR applications. All these applications belong to different categories. And these are the system parameters for our systems and for our servers and clients. Now, we will talk about the accuracy of Intelligent Client. This figure shows the round-trip time distribution of Intelligent Client and human players of 6 benchmarks. The x-axis shows 6 benchmarks, and the y-axis shows the RTT distribution. Let's take STK for an example. STK-IC denotes Intelligent Client, and STK-H denotes human players. From the result of STK, we can find that the distribution of RTT are very similar. For other applications, D2 has the maximum difference, but it's still within 4%. So from this figure, we can conclude that our AI client has high accuracy and it can mimic human players faithfully. Next, we will evaluate the performance of our Intelligent Client. The blue bar is CV time on the left side, and the yellow bar is input generation time on the right side. And the x-axis shows the 6 benchmarks. From this figure, CV time is about 80 milliseconds, and the input generation time is about 2 milliseconds. As a result, our Intelligent Client can generate 800 actions per minute, which is fast enough to simulate professional game players, 300 actions per minute at maximum. Now, we will evaluate the overhead of picture framework. The x-axis is benchmark rate, and the y-axis is FPS reduction with picture. From this figure, we can learn that STK and ITP has the highest overhead, but still less than 6%. And the average FPS reduction is only 2.7%. So picture framework has low overhead. Until now, we have talked and proved that the AI client is fast and accurate. Picture framework has low overhead. Next, we will use them to analyze Cloud 3D system. This slide shows the CPU cycle breakdown. The x-axis are benchmarks, and the number on the x-axis indicate how many instances of same game are running simultaneously. And the y-axis on the left side is the CPU cycle breakdown, and the y-axis on the right side is IPC, instruction per cycle. From this figure, we can learn that IM has the largest portion on front end comparing to other applications. This means IM has problems on instruction fetching. Also, the backend cycles grows when we increase the number of game instances, which means the contention is on the backend. We will talk about the resource efficiency in this slide. The first figure shows the average server IPS and client IPS when running 1 to 4 instances of same game. From this figure, we can learn that one GPU can serve 2 to 3 games while maintaining FPS above 25. And the second figure shows the poor usage per game instance. From the second figure, we can learn that poor consumption per game decreased significantly as we increase the number of game instances. So from these two figures, we can conclude that cloud gaming has better hardware and energy efficiency. This slide shows the breakdown of round trip time into server time, input send frame time, and send input time. The x-axis is benchmarks, and the y-axis is latency in milliseconds. From this figure, we can learn that server time, the blue bar, dominates the RTT, indicating cloud system and hardware design is crucial to cloud 3D performance. In order to find the bottleneck of a server, we further break down the server time into 4 parts. And from this figure, we can learn the application is most time consuming. So we will further break down the application time. This figure shows the breakdown of application time. The green bar is the time spent on application logic, and the yellow bar is frame copy time, and the blue bar is the rendering time for a frame. Since the application logic is runs in parallel with GPU rendering, so application time is actually decided by application logic time plus the frame copy time. So from this figure, we can learn that frame copy time, the yellow bar, accounts for more than half of the application time in most cases. So frame copy should be optimized. Now we can draw the conclusion that Picture is an effective benchmarking framework for identifying bottleneck of cloud 3D system. Although we have already found the bottleneck of cloud 3D system using Picture, we can do even better. Based on our experimental results, we propose 2 optimization, catching frequently used results and increasing parallelization. For these 2 optimizations, you can read our full paper for more detail. From our evaluation, our optimization could improve server FPS by 57% on average and 115% at maximum. The client-side IPS was improved by 7% on average, and the RTT was reduced by 8% on average. Now, let me quickly conclude. Evaluation shows Picture has low overhead and high accuracy, less than 3% on average. Latency on the server side dominates the round-trip time, indicating hardware and system design are crucial to cloud 3D performance. Also, our optimization on frame copy bring 57% speed up. Thank you for your attention.